Yesterday we talked about energy, shifted gears from forces to energy, and it's not like the two are unrelated to each other. In order to have energy, we need a force to accomplish that. We'll talk about that a little bit more probably tomorrow. But we defined energy in general as the ability to do work. Sometimes energy is doing work right now, sometimes it's just stored and has the potential to do work later on. If it's doing work right now, then it's because something is moving. We define that as kinetic energy, energy of motion. And kinetic energy is given by the equation 1/2 mv squared. This is a general equation that applies to anything that is moving, right from the scale of an electron orbiting around a nucleus to a planet orbiting around a star. Anything that's moving and has mass has kinetic energy. We can find its value of kinetic energy by using the equation 1/2 mv squared. M stands for what? Mass, and it's measured in kilograms. Sometimes we're given a mass in grams. If you want to convert it from grams to kilograms, what are we going to do? No. We're going to divide it by 1,000. That's the kind of thing that sometimes we get mixed up with, multiply or divide by 1,000, right? That's okay. But if you do happen to get mixed up with the conversion there, you should catch yourself, because we always should, when we do something like that, stop and see if our number is realistic. Okay? If I was to go home tonight and I was to cook 1 pound of ground beef so I could make, let's say, soft tacos, okay? So I'm making soft tacos, 1 pound of ground beef. 1 pound of ground beef is exactly 454 grams. It'll say that in the package, 454 grams. Well, I want to convert that to kilograms. Okay, let's try multiplying it by 1,000. What do I get? 454,000 kilograms. Does that make sense? Is that a reasonable number? Am I cooking 454,000 kilograms of beef tonight? No. It doesn't make any sense, right? So if you multiply by 1,000 as opposed to divide by 1,000, that's okay. Just make sure that you catch that mistake, because you've checked to see if the number you get is a reasonable number. All right, so divide by 1,000 if that happens to us. All right, what does V stand for? Speed as opposed to velocity, because we don't need a direction here. It's measured in meters per second. The most common unit for speed that we're given other than meters per second is kilometers per hour. How do you convert kilometers per hour to meters per second? Yeah, you're going to times it by 1,000, and then you're going to divide by 3,600. Good. Kinetic energy is measured in what units? Joules. And kinetic energy is a vector or a scalar? It's a scalar. In fact, as we go through this unit, you're going to find that all types of energy, kinetic, potential, and then the subcategories of potential energy, they're all scalars. Okay? There's never any direction associated with energy. All right, we talked about the other type of energy yesterday. That's potential energy, which is stored energy. It's not doing work right now. It just has the ability to do work, or the potential to do work down the road. If you have potential energy, then you have energy that can at some point make something move, at some point be converted to kinetic energy. The two types of potential energy that we mentioned yesterday, or that we focused on yesterday, were gravitational potential energy. Gravitational potential energy is the energy due to an object's height above the ground or above something else. The other type we talked about, not in a lot of detail. We'll talk about this in more detail in our next unit, but just mention it for now. It's elastic potential energy or spring potential energy. Let me write that so it's a little bit easier to read. Elastic or spring potential energy. Again, for now, gravitational potential energy is our focus. The equation for gravitational potential energy is this. EP is equal to mgh. What does M stand for? Mass again, and we do the same conversion that we do with the mass in kinetic energy. It's always measured in kilograms. G is acceleration due to gravity. We said yesterday 9.81 meters per second squared, usually, although it could be something different. If you're high up in a mountain, it could be like 9.78. If you're on another planet, it could be dramatically different. But we'll say 9.81 because usually we're on the surface of the Earth. What does H stand for? This is going to be the height, and that's going to be measured in meters. Now, remember what we said yesterday as well, that the height can be measured relative to whatever we want. The height of this board marker right now relative to the floor is about 1.5 meters. Relative to my hand, it's 0. We can define it relative to the floor or my hand, whichever one is most convenient. Okay, and you'll see as we go on and do some calculations with potential energy later today, how exactly we do that. Remember that all of these numbers here are positive numbers, even the G, 9.81 meters per second squared, because potential energy is a scalar. We always want positive numbers making up that scalar value, that potential energy. All right, yesterday we had 3 questions for homework. I want to take a look at those 3 questions right now on page 303. Let's have a look at 2 and 3 here. Number 2 says a car traveling at 80 kilometers per hour on a highway has a kinetic energy of 4.2 times 10 to the 5 joules. What's the mass of the car? Let's write down some givens for this. We're going to say that the speed is 80 kilometers per hour. We're going to draw attention to the fact that it's kilometers per hour because we know we're going to want to convert that to meters per second. We'll deal with that in a minute, though. The kinetic energy is 4.2 times 10 to the 5 joules, and we're looking for the mass. Now, some of you like to solve for sub your numbers in and then solve for the value you're looking for. I usually, not always, but usually like to solve for the variable that we're looking for right away and then sub my numbers in. It doesn't really matter which you do, but I'm going to show you how to solve for m before I sub the numbers in. Okay, we got to get rid of everything that's not attached. Well, everything's attached. Let's get rid of what is attached then. What's attached to the m? A half and the v squared. Okay, the half and the v squared are both multiplied by m, so how do I take them over? I divide. So we're just going to say ek over 1/2 v squared is equal to m. Some people like to try to square root this because we see a square for the v. The only time you're going to square root this is if you're solving for v. You don't need to square root something if you don't need to get rid of the square. And if we're not solving for v, then we don't need to get rid of the square. So this is the rearranged form of it. M is equal to 4.2 times 10 to the 5 joules divided by 1/2 of v squared. Okay, what is 80 kilometers per hour to meters per second? 80 times 1,000 divided by 3,600. I think it's 22.2. Yeah, go ahead. Yeah. 22.222 meters per second. And then, of course, we've got to square that. When we do the math there, we should end up getting the answer that's in the book, which is 1.7 times 10 to the 3 kilograms. How come we used two digits in our final answer? Yeah, look back at your data. This is how many digits? The 80. It's 3. This is how many digits? 2. How many digits should the final answer be? 2. Even if one of them was 16 digits, we always go to our least precise piece of data, which in this case is the 4.2 times 10 to the 5, the 2 digits. Final answer gets rounded to 2. The rules for significant figures are kind of like that expression you've heard. A chain is only as strong as its weakest link. Have you ever heard that? Chain is only as strong as its weakest link. So what that expression means, and it's so true, if you have a chain with 20 different links in it, and 19 of them are incredibly strong, but one of them is weak, then the chain is going to break, right? Because you have a weak link in that chain. Okay, here we use that analogy here. We'd say that an answer can only be as strong as its weakest piece of data. It can only be as precise as its weakest piece of data. So you can have a really high degree of precision for speed, but a really low degree of precision for energy. Well, your answer is going to have a low degree of precision. Your answer can't be more precise than your weakest piece of data, any more than a chain can be stronger than the weakest link in that chain. So it is 2 digits. All right, number 3 says a skateboarder with a mass of 65 kilograms increases his speed from 1.75 meters per second to 4.2 as he rolls down a ramp. What's the increase in his kinetic energy? We're going to say that the mass here is 65.0 kilograms. We're going to say that something is 1.75 and something is 4.20. What's the something? What's the first something? VI. This is how fast it's moving initially, VI. We'll call that speed because it doesn't give us direction here. The final speed is 4.2 meters per second. We want to find the increase in kinetic energy. Increase is the same meaning as the word change. Change is given by what symbol? Delta. So we're looking for delta EK. Now, here's what I do not want you to do. Do not say, don't even write this down, okay? This next step down, because I'll erase it in a moment here. Do not say delta E is equal to 1/2 of delta V squared. That doesn't work. That's not an equation. I didn't show you that equation. It's because it's not an equation, not a valid one at least. It doesn't work. What we can do is use our regular kinetic energy equation that we learned yesterday. EK is equal to 1/2 mv squared. But because we're looking for delta EK, what I want to do is say 1/2 mvf squared minus 1/2 mvi squared. Final minus initial kinetic energy. You can subtract kinetic energies. You can't subtract speeds when you submit that equation. 1/2 of the mass of 65 times VF, which is 4.2. Don't forget to square it. Minus 1/2 of 65 times VI, which is 1.75. Don't forget to square it. Do the math there, and we should end up getting 474 joules. And that's given to us in 3 digits. Why 3 digits? Well, look back to your data. This is 3. A 0 on the end counts as a digit. A 0 at the beginning does not count. This is 3 digits because it's on the end. This is 3 digits. This is 3 digits. Final answer should be 3 digits. The weakest piece of data, the weakest link is 3. Therefore, the answer is going to be only as strong as that weakest link, which is a 3-digit link. All right, let's move on now and talk about the other type of energy, potential energy, specifically gravitational potential energy. We briefly defined it yesterday and during our review today, but we're going to provide a little bit more detail here now. Gravitational potential is the energy stored. Of course it is. Any kind of potential energy is energy stored. Gravitational, elastic potential. We talked about chemical potential briefly yesterday. Electrical potential. It's the energy stored. This time, though, it's in an object due to its height. Now, this is important sometimes at least. The fact that gravitational potential energy is always measured relative to something. We said earlier during our review that the potential energy of this board marker right now relative to my hand is 0. But relative to the floor, it's something. Because there's a height relative to the floor, but no height relative to my hand. It doesn't matter what we define the potential energy relative to, as long as we specify. It's 0 joules relative to my hand. It's 28 joules relative to the floor, whatever the case may be. We can pick the reference point. We can define it relative to whatever we want, as I say, as long as we specify. Now, clearly, from the equation that we learned a few minutes ago, the bigger the height, the more potential energy you have. And that should make some sense to us, right? Some logical sense. If you have an object that is higher up, there's more potential to fall. There's more potential to do work. If you drop a coin off the edge of the Empire State Building, okay, it's going to have a lot more kinetic energy when it reaches the bottom than if you drop a coin off the edge of your desk. The bigger the height, the more ability it has to do work, and therefore the more potential energy that it would store. I'll write in the equation again, although I've already done that. EP is equal to mgh. Remember to make m in kilograms, h in meters, and remember that g is, we're going to make it positive 9.81 meters per second squared, or whatever it happens to be, whatever gravity happens to be at the location that you're at. Yep, Ben? All right, let's take a look at example 6.3 on page 298 that relates to gravitational potential energy. It says figure 6.14 shows a toy car track set up on a tabletop. Question A says, what's the gravitational potential energy of the car relative to the floor? Now, I could, if it didn't say relative to the floor, define the potential energy relative to the tabletop if I wanted to. But in this case, I can't because it specifies my reference point. If I want to find my potential energy relative to the floor, then I'm going to use this equation using the height relative to the floor. The mass is 0.0250 kilograms. I don't need to convert that because it's already in kilograms. G, we're going to assume is 9.81 meters per second squared because presumably we're on Earth. And H is, relative to the floor, the car is 2.15 meters up. Now, relative to the tabletop, it's what? 2.15 minus 0.95? So what would that be? I think 1.25, I think, something like that. If we were asked to find the potential energy relative to the tabletop. But we're not. So we'll use the 2.15 meters relative to the floor. Multiply those numbers together, what are we going to end up getting here? .25 times 9.81 times 2.15. I get 5.272875. Why am I writing down this number with 6 decimal places? Is that a mistake there?
Yeah, 0.0.
Oh, so what is the answer there? 0.52. Okay, thank you. Why am I writing down this number with 7 decimal places? Just in case I need that for question B. Now, as a final answer, question A should be rounded to 3 digits. Okay, 9.81 is 3 digits. This is 3 digits. Notice the numbers the zeros at the front don't count as significant digits. The zeros at the end do. So that's 3 digits. Final answer should be rounded to 3 digits, 0.527 joules. Look at the 3 digits here, and then look at the digit right after that. It's a 2. It rounds down, 0.527 joules. But we wrote down the unrounded number just in case we needed to solve B. Let's solve B now. It says, what's the change in gravitational potential energy of the car when it arrives at the bottom of the hill? Delta EP is equal to mgh final minus mgh initial. Mgh final is 0.0250 times 9.81 times, well, the final height is 0.950. What's the mgh initial? Save yourself some work. What's mgh initial? 0.5272875. We already calculated mgh initial, right? We don't need to calculate that again. That is, as long as we kept the unrounded number up. Let's say 0.025 times 9.81 times 0.95 gives me 0.2329. Subtract, what was my number? 0.527, 2875. Gives me a value of negative 0.2943. Negative 0.2943 joules. Let's round that to 3 digits. What would that be in 3 digits? Negative 0.29? Is that 3 digits? That's 2 digits, right? The first 0 doesn't count. Let's look at 3 digits here. It's 0.294. Then let's look at the digit right afterwards. That's a 3. It's going to round down to 0.294. Can anybody tell me what that negative means? Remember we said that energy is a scalar. That negative does not mean left. Usually for us, a negative means left or down or south, right? What does it mean here, Ben? Yeah. So in other words, what's happened to the potential energy? It's changed. It's lost. We've lost potential energy. Okay, delta energy, delta E, either potential or kinetic, is going to be positive if you gain, negative if you lose. It has nothing to do with direction. It has everything to do with gained or lost. So you're never going to get an EP that's negative, but you can get a delta EP that's negative because we lost potential energy there. All right, let's have a look at a few questions that go along with that. I'm going to put a little star by number 3, because this one's a little bit tricky. Okay, I'm not going to do this for you, but I will kind of give you a little bit of help on this one. Here we have an inclined plane air. This is not going to be one of those questions where you have to find F parallel and so on. You want to find the change in potential energy. You need the height. If the ramp is 20 meters long, how are you going to find the height there? Yeah? Yeah, you got to do some trig, right? You don't need to find F parallel or Fn or Fg or anything like that. All you got to do here is find the height, because potential energy is dependent upon the height. So get that height and then find the change in potential energy. All right, let's get to work on these 3 questions. Let's have a look at question number 1. It says a pile driver drops a mass of 550 kilograms from a height of 12.5 meters above the ground into the top of a pile that's 2.3 meters above the ground. Relative to the ground level, what's the potential energy of the mass at its highest point, at its lowest point? And then we want to find the change in the gravitational potential energy as it's lifted from the top of the pile to its highest point. Let's do this now. Question number 1 here. We want to find the potential energy, the gravitational potential energy at its highest point. So we're going to say EP is equal to mgh. The mass of this pile is 550 kilograms. G is 9.81, and the height of this pile, let's see, it says height of 12.5 meters above the ground. We're going to say 550 times 9.81 times 12.5 should give me, I presume, 6.74 times 10 to the 4 joules. There's the potential energy relative to the ground of the pile when it's 12 meters up. Well, then we simply use gravity to drop the pile and let it do its thing, right? Gravity is, well, gravitational potential energy is stored energy, the ability to do work. We let it go, and it starts doing work. It starts being kinetic energy. We want to find its potential energy now at its lowest point, which is 2.3 meters above the ground. 550 times 9.81 times 2.3 meters. We multiply those together, and we should get 1.24 times 10 to the 4 joules. What's the change in potential energy of the mass as it's lifted from the top of the pile to its highest point? Do you think it should be a positive value or a negative value? It should be positive because we're gaining potential energy, right? If we're talking about the change in potential as it fell, it would be a negative delta E because we would be losing energy. Just 1 second. Let's say delta E is equal to final energy minus initial energy. If we're raising it, the final energy is 6.74 times 10 to the 4. The initial energy is 1.24 times 10 to the 4 joules. We really should use the unrounded numbers there. I don't know what they are because I just copied the answer from the answer sheet. But you should use not the 6.74, but the unrounded version of that. When we do that, it works out to be about 5.50 times 10 to the 4 joules. The energy gained as it goes up, 5.5. If we were to solve for the energy, the potential energy lost as it fell, what do you think it would be? Negative 5.5 times 10 to the 4 joules. Yeah. Let's take a look at number 2, and then we'll leave you with number 3 for a few more minutes. Number 2 says a roller coaster trolley begins its journey 5.25 meters above the ground. As the motor tows it to the top of the first hill, it gains 4.2 times 10 to the 5 joules of potential energy. The mass of the trolley and its passengers is 575. How far is the top of the hill above the ground? Okay, let's say that its initial height is 5.25 meters. We're going to say delta E, this is the change in potential energy, is 4.20 times 10 to the 5 joules. This is not E. This is not the potential energy. This is the change in potential. It's 4.2 times 10 to the 5. The mass of the object here is 875. We want to find the final height. How far the hill is, the top of the hill is above the ground, okay, after this trolley has gone up. So let's say delta EP is equal to mgh final minus mgh initial. Right? Potential energy is mgh. Delta potential energy is final minus initial. Well, we know what delta E is. It's 4.20 times 10 to the 5. M is, what is M? 875 times 9.81 times HF minus 875 times 9.81 times HI. HI is 5.25 meters. There we go. There's only one variable I don't know there. The math's a little bit tricky here, but let's do this. Let's calculate that number on the right-hand side. 875 times 9.81 times 5.25. And this number is 45064.6875. 875 times 9.81 is 8583.75 times the final height. What are we going to take over first? The 8.5 or the 4.5? 4.5, because it's not attached, right? Take over what's not attached first. And we're going to take that over by adding. So it becomes 4.2 times 10 to the 5 plus 45064.6875. And then we're going to divide by 8583.75. We get an answer of 54.2. $54.2 meters. Now, some of you got an answer that was like 48 or something like that. Well, where does that come from? If you said EP is equal to MGH, and rearrange that, EP is equal to, or H is equal to EP over mg, then you get an answer of something like 48. 48 point something, I think it was. But that's not right. You understand why that's wrong? Look, the final potential energy is not 4.2 times 10 to the 5. That's not what the potential energy is. That is relative to the ground, at least. Relative to the ground, that's the change in potential energy. We don't know what the initial was, but it was something. So we can't just say H is equal to EP over mg when that's not EP. Okay, that says, the question says that's the gain in potential energy. So what we want to do is set that equal to delta E, not to E. Yep.
If you added 5 places, 5.5
Yep.
5 versus 5.25.
Right.
If you added that to the 48.
Yeah, 48 point whatever. Yeah, if you add it to it, that's right. Because understand what you've solved for here. Okay, technically that's, that would be delta EP. So you would have solved for the change in height. Not the height, but the change in height. Now, if you solve this way in black there, use it and find the change in height, well, that's not the final. If the initial was 5 and the change is 48, then you better add the initial to whatever you change by, and then you're going to get the right answer, right? So it's a slightly different way of doing it. They're both correct, but what we've done just there in black is not correct, okay? Because it's not the height, it's the change in height if we're going to do it that way. All right, let's keep working on number 3 here, and then we'll take a look at that one in a few minutes if we need to. All right, let's have a look at question number 3 now. This one says a winch, which is kind of just a motor that pulls a cable that hooks onto something and kind of almost tows something out. A winch pulls a 250 kilogram block up a 20 meter long inclined plane that's tilted at an angle of 35 degrees to the horizontal. What's the change in gravitational potential energy that the block undergoes? Let's draw this out here. Here's the inclined plane. It's 20 meters long. There's an angle here of 35 degrees. This is not a question where we're going to do the F parallel or anything like that. Look, all we're going to use here, all we're going to use this angle for is to find this height, the final height of this block as it goes up this inclined plane. So let's do that now. Let's say sine 35 degrees is equal to opposite, that's the final height, over 20.0 meters. That's the hypotenuse, or the length of the incline. What does that equal? Does anybody have that calculated, 20 sine 35? 11.47 meters, thank you. So there's my final height. If I want to find the change in potential energy, I'm not going to say EP is mgh, rather I'm going to say delta EP is equal to mgh final minus mgh initial. Does that make sense? Because it's change, right? Change, gain in potential energy, loss of potential energy, they all mean the same thing. Now, this does work out kind of handy, actually. What's the initial height? 0. So m times g times 0 is 0. The change in energy ends up being the same value as the final potential energy. But I would like you to tackle this question like this, thinking mgh final minus mgh initial, so that when the initial height is not 0, you know how to do it, right? If the initial height wasn't 0 here, okay, then the final potential energy wouldn't be the same as the change, like it is in this case. All right, let's calculate that now. M is, what is M here? 250 times 9.81 times the final height, which we just figured out is 11.47 meters. And technically that's minus 0. But when we do that math, it works out to be the same value, 2.81 times 10 to the 4 joules.